about measuring power where inverter drives are involved. And I mentioned that so a lot of my experience was with refrigeration compressors. Sometimes we would measure the power going into the inverter. Sometimes we try to measure the power coming out of the inverter going to the compressor, and both have their issues, I'll say. Sometimes you think that, well, gee, I can measure just the AC power coming off the AC lines going into the inverter, and that'll be easy. I'll have to discount the power loss in the inverter or whatnot if I want to see what gets to the compressor, but we'll talk about both sides of the inverter. Why do people want to use inverters? Because it's a very easy way to modulate the capacity of a piece of equipment being driven by an electric motor. You can improve the efficiency of your product by matching the capacity of the product to the load. And again, I'm kind of referring to refrigeration compressors, which I have a lot of experience with. So if you can match the refrigeration needs to the compressor capacity by modulating the frequency, then you get the best efficiency. Capacity, as I mentioned, is proportional to the speed or the revolution per minute. So if you're moving the piston up and down, the faster it goes, the more gas you need. In the compressor business, at least 20 years ago when Bob and I were working there, most of the hermetic compressors were two-pole motors. And two-pole motors run at basically synchronous to the line frequency, and that's 60 cycle here, so that's 3,600 cycles a minute or 3,600 RPM. They run a little slower than that because of slip frequency or something like that. I'm not a motor designer, but basically a two-pole motor runs synchronously with the frequency of the power line. If you want to cut that capacity in half, if you were able to reduce the frequency by half or to 30 hertz, then it's running at 1,800 RPM and you got half the capacity. So it's a real easy way to modulate the capacity. What do we do?
Page down, lower right hand corner there.
Page down. Okay. Lower capacity, lower frequency, and accompanying it, lower voltage. I'll say a little bit about that in a minute. Higher capacity, higher frequency, higher voltage. Just kind of a side issue on the magnetic side. If you want to take a transformer that you bought it for a 60 hertz application and decide you want to use it at 50 hertz, you have to reduce the voltage proportionally. So, if you take a 60 hertz transformer or 60 hertz magnetics and you reduce the voltage by 5, 6 if you want to, or 2, 5, 6, then everything continues to work, not overheat and burn up. Another way of saying that is the volts per hertz need to be constant. I'll go through this real quick. I just wanted to show where some of these things came from. I mean, watts is very easy to define when you're in the DC world. It's just voltage times current. So if it's DC, volts times amps, no problem. In the AC world, it gets a little more complicated. Now, it's still volts times amps, but it's you have to take into account the sinusoidal nature. So if you multiply a voltage sinusoid times a current sinusoid, that's shifted a little bit relative to the voltage. You work through the math and you basically get the sum and difference frequencies. So if at 60 hertz, the sum is 120 hertz and the difference is 0 hertz. Well, 120 hertz has the average value of 120 hertz is 0, so it has no power associated with it. But the difference frequency is 0 hertz, and that's basically DC, and that's where the power is realized. So you work through all of this, and you basically get the RMS value of the voltage times the RMS value of the current times the cosine of the phase shift between them. And if there's no phase shift, that becomes 1, and it becomes V times A, but that's only true for a sine wave with no frequency shift between them. So just be aware of that. We sometimes oversimplify. You think you can take a voltmeter reading with a voltmeter and an ammeter reading with an ammeter and multiply them together. Well, you got VA, which will only equal the power if there's no phase shift between. Just a little bit about what frequency components makes up a synthesized wave. We just drew out a 120 volt RMS 60 hertz wave, and it's 120 volts. And if you think about it, it's 120 volts RMS, because if you rectify this thing and take a minus 120 and put it up here like you would in a rectifier, then it becomes 120 volts DC. And, so it's pretty easy for a square wave, like I've drawn here, to know what the RMS value is. If you do the frequency response of that square wave, you find that, lo and behold, there is a component at 60 hertz, but it's only the equivalent of 54 volts RMS. So 120 volt square wave produces 54 volts RMS of 60 hertz, and then a decaying group of harmonics that are multiples of the 60 hertz. And they're odd harmonics, so 180, 300, 420, and so on, that decays off. Why do people, one of the popular converters is pulse width modulation, or PWM converter. The reason that they're so popular is that the harmonics, unlike what I just showed you, that are multiples of the 60 hertz frequency that you were interested in, the harmonics become multiples of the PWM, I call it carrier frequency, or the modulation frequency. And if that modulation frequency is in the 8 to 10 kilohertz range, which it typically is, or even higher, then the harmonics that are created are multiples of this frequency. So now you got harmonics that, you know, if the PWM frequency is 10 kilohertz, your highest harmonic you have to worry about is 10 kilohertz, and the next one's 20 kilohertz, and 30 and 40, and so on. That's a lot easier to filter out than 60 and 180 hertz and things like that. So that's why people like to use PWM inverters at high frequencies, because you can filter, you can handle the harmonics more easily because they're in high frequencies. So I've just drawn a very simplified system here where you have an input voltage, typically 60 hertz. You full wave rectify it. And then there's some inverter logic that creates this PWM waveform that then goes to the motor. So we're going to talk more about how we measure the power over here and what happens, and also how we measure the power over here and what happens. I'm going to break this down. This is a pretty busy chart, but these green areas here are the PWM carrier frequency. So this part is modulated to create the positive part of an AC sine wave. This negative part here is modulated to create the negative part. And we actually put this together using SPICE. A lot of times when we're working with people, we need to simulate their waveform and whatnot, and it's sometimes we can do it in SPICE, and sometimes we actually do it on an Excel spreadsheet. Believe it or not, you can capture waveforms and things. Maybe you've done this, but you can capture waveforms and things with some of the scopes and things that you have available to you today. Read that into Excel and do your analysis in Excel. Kind of proof that what you thought should work does actually work. But what I wanted to show on this is this is the PWM. It basically switches between the plus voltage, and we just chose 1 volt to make the analysis simple. But it basically switches between plus 1 volt and minus 1 volt and 0. So during this period of time, I'll jump over here and then maybe I can jump back. This shows you that period of time. So when you're near 0, you have the 1 volt on for a very, very short period of time. And then as you want to increase the voltage the period of time that it gets on, gets wider and wider and wider until you're at the peak of the sine wave. This sine wave is what we use to synthesize the duty cycle of the PWM. So this is a 0.9 volt sine wave that we use to modulate this plus minus 1 volt signal. We then filtered the resulting output. So if I go back, and I go back with the back arrow?
Mm-hmm. Okay, there you go.
Basically, I would have this type signal going to my compressor if that was my load or whatnot. If I want to measure that, that's the signal I'm looking at. And if you want to, it's synthesizing a 60 hertz wave, which is basically this wave. What we did here was we put that through a low pass filter, and this is what we get out. So that's what the compressor is trying to run on. And I know you can't see it here, but there's actually two waveforms there. Kind of tell here it's a little bit broader line. We actually filtered this waveform, and then we also put this signal that we created this waveform through the same filter, and to prove that they do indeed coincide. Things you need to remember. Here's our PWM. It switches at, in this case, 1 volt, but let's say you're a 120 volt system. It's got to have a voltage to create the peak of the sine wave. So the peak of a 120 volt sine wave is 160 something. So typically a PWM system is going to have a rail voltage of a couple hundred volts in order to synthesize a 120 volt AC signal. So you got to be able to contend with a couple hundred volts peak voltage. These lines represent what you would get if you measured the RMS of this. So for this signal here, we have 0.76 volts RMS, but in fact, you probably only wanted to know what the 60 hertz component was going to your compressor, because that's what's going to put energy into the compressor, and, or you know, I keep saying compressors. It could be a clothes dryer or washing machine, and there are lots of appliances and things now using inverter drives. And I'll say more about clothes dryers and dishwashers. Believe it or not, most of the dishwashers and clothes dryers have inverter drives in them. That's how they match the capacity needed to do a good job of cleaning clothes or cleaning dishes to the application. So, you know, I've had people in the compressor world, and we deal with other people other than just Copeland, carrier trained. Quite often they'll come and say, well, I want to know what the RMS value of this waveform is. Well, as we were talking, do you really? I mean, you might, depending on what you're trying to accomplish with your measurements, but if you're interested in what voltage is being applied to the compressor to do work, it's the 60 hertz component in this example. So the 60 hertz, or I call it the fundamental, in this application was only 0.64 volt RMS, where the total power in the PWM waveform was 0.76. So you got to ask yourself, what do I want to measure? What am I interested in?
Since you're interested in the 60 hertz portion, the question becomes is, are you filtering out the rest of it where it doesn't matter when you're on the output? Or is it all still there? Is all that little harmonic still there?
Yep. Okay, you gotta in again, the compressor world, or if you have a motor, there's enough inductance in the motor that typically the harmonics are filtered by the inductance of the motor, so you don't have, I'm just saying typically, but you gotta look at your application. Typically, there are not a lot of harmonics in the current, but there sure are in the voltage. So you literally see this being applied to the compressor motor. But the current will look pretty sinusoidal. And I'm sorry, I kind of lost your question. But
well, if I'm looking at the RMS, and and my motor is filtering out the harmonics, then I'm really, when I look at it, I'm seeing 60 hertz, and the RMS is what I'm wanting to see. But if it's not filtered out, then it's going to alter the voltage I'm seeing on my meter. That's what I'm trying to.
And I had a fellow do this. He says, you know, before we had inverters, I had this triplet meter, or Simpson meter. I had a Simpson 260. I mean, you know, some of us are old enough to remember Simpson 260s. I just want to take my Simpson 260 and stick on that voltage line and see the same voltage that I used to see. Well, I'm sorry. You can't do that because the RMS of this, which is what the voltage waveform is higher than what the 60 hertz filtered component is going to the compressor. So that's why I say you got to know what's your motive in making this measurement to know what value you need to measure. Now, well, I'll get to it in a minute. Strangely enough, the average value of this is the filtered version, and if you use an average responding meter instead of an RMS meter, I mean, we're all taught, oh, let's get a good meter, let's get an RMS meter. Just understand what that's giving you. It's giving you the RMS. If you want to know the fundamental, it's actually the average. So if you had an absolute average responding meter, you would see what you used to see with your Simpson 260. Thanks for the question. We have multiple types of transducers. There's more than one way to measure watts. And you need to know something about the way, if you're using a watt transducer, you need to know something about the style of transducer that you have. We have transducers, and these are our particular model numbers that I'll refer to later, that use what's called pulse height, pulse width modulation. It basically takes the voltage and makes a pulse, an electrical pulse, whose height is equal to the voltage. And then it makes the width in time proportional to the current. So now I've got a pulse whose height is voltage, whose width is current. And what's the area of the pulse? The product of the two, power. So if I sum up all those pulses over time, I got average watts. So there are a number of, this was a very popular technique 20 years or so ago, and there's still a lot of transducers out that do that. It's a pulse height, pulse width multiplication. I'll say the buzz now, and for the last 10 years or so, are digital signal processors that can actually sample the waveform many times an electrical cycle, sample both voltage and current, and do a point-by-point multiplication. And then sum up all of those and take the average. And we make that product as well. We call them DSPs, for digital signal processing type devices. And then there's another way of doing it, and I don't know whether people will understand this one or not, but this really goes back several years. There's a thing called a Hall generator that is a magnetic field sensor, and you put a current through the Hall generator, and you put the Hall generator in a magnetic field, and the output of the Hall generator is the product of the current through the Hall generator times the magnetic field that it's in. That's watts. If the current is proportional, say, the current in your system, and the magnetic field is proportional to the voltage in your system, you expose a Hall generator to that, and you've got a very simple device that does the multiplication, and it's true watts. It does a true multiplication. There's no sampling error. It really is a true multiplication. And we have a product called the PC5 that operates on that principle. Here's just the words that I told you. Pulse height, pulse width creates a series of pulses that are equal to watts. Digital sampling, as we talked about, DSPs. Ours run at about 20 kilohertz, so I forget the exact number of samples, but that gives you a couple hundred samples at least in a 60 cycle waveform. There's a lot of products out there running faster than that nowadays. And then our analog multiplier, the Hall effect generator, and it takes into account phase shift as well. So like I say, it is a precise, accurate multiplier. We were working with some people measuring, building test stands for measuring washers and dryers, as I mentioned, that had inverters, and they called us up and said, your transducers are not giving us the right answers. So we went down to see what the problem was, and what we found was that they were measuring the current, and they had a clamp-on ammeter, it was a true RMS meter. And they said, well, my gosh, I got a 5 amp transducer, and I've got my clamp-on ammeter, and I'm only putting 3 amps into your 5 amp transducer, and it's not measuring right. Well, that current signal, I'm going to talk about in a minute, had a crest factor of 5.8. Now, most of you know that the crest factor for a sine wave is square root of 2, 1.4. So basically, the peak of a sine wave is 40% higher than the RMS value that you would measure. This thing was almost 6 times bigger, and I'll show you why in a minute. So it was saturating or clipping in our transducer and not giving the right answer. I talked about pulse height, pulse width. You have to do that at a certain rate, and our transducers that did that did it at a rate of between 1320 and 1380 hertz. And that happened to be very near the 22nd or 23rd harmonic of the signal, and we got a beat frequency, and I'm going to show you in a minute what that is. Now, it didn't make the measurement inaccurate, it made it hard to read because it had a beat frequency on it, and it was varying in time. So as you tried to look at it on your meter, you'd see it go up and come down and go up and come down. You say, well, what's the right answer? You know, the average is the correct value, but it's still hard to look at because of that beat frequency. And it had a beat frequency because our GW, which I told you did this pulse height, pulse width modulation, did that at a frequency that was near one of the harmonics in that waveform. So by adjusting our frequency so it was right in between these two, we could solve the problem and make it work in this application. Just something you have to look out for. Again, we use SPICE. So here's a SPICE model that just uses a bridge, and we just use a resistor as a load. And this is what I wanted to show you. Here's our voltage, but this is our current. And that's what I was saying. The current waveform had a very high crest factor. If you think about it, if you have a rectifier charging the capacitor, it only charges the capacitor at the peak of the waveform. So it's only drawing current and recharging the capacitor to replace whatever charge came off, you know, during the rest of the cycle. So you get a current waveform that looks like this. It's not a sinusoid, and it has a very high crest factor. And it gets worse the lighter the load. So this is something to look out for. You know, the people that were doing this thought, oh, I'm on the AC side of this rectifier. Ought to be a nice sine wave. No, it's not. In fact, they were very helpful in helping us get to the bottom of the problem, and they did this analysis on their current waveform, and this is the harmonics that were contained in that current waveform, and this is some data that our customer actually took to show what the harmonics were in that current waveform. So what we did was we took our transducers. This is a particular model of one of our transducers, and it's the Hall generator type. And we used one of Hewlett-Packard's programmable signal sources. We took that waveform that I just showed you, and we programmed it into the signal source. so that we could create a current that was exactly like the current that they were trying to measure, and we put it into our PC5. Now, kind of small up here, but this current waveform had a RMS value of 1.7 amps, but yet it had a peak value of 5.8 amps. So this was low enough that our transducer could handle the peak of that without saturating. And again, we put this waveform, both of these waveforms, into Excel like I was telling you could do. And we just did a point-by-point multiplication in Excel. And that said we should, with these two waveforms, see 256.7 watts. So that was just an Excel calculation based on these waveforms. In fact, our transducer measured 251 watts, so we were 2% light. Not too bad. I guess I'm showing you that to say it did a pretty decent job of measuring that waveform. And again, we looked at the output, none of this beat frequency business, just kind of high frequency hash that you quite often get. We did the same thing on the digital sampling. Believe it or not, we got about the same offset, and I'm beginning to wonder if the offset isn't something to do with maybe I synthesized the waveform just a little bit off. I might have had a slight offset in my calculation, because all the transducers that I measured were off about the same, minus 2%. We did another test as kind of a reality check on our DW5. From the last slide, we set our the RMS value of this was like 2 amps or something like that. So we actually put in a sine wave of the same RMS value and got the same results. So again, we kind of use Excel spreadsheets, different techniques for a reality check transducers. Again, no, just kind of high frequency hash on the output, everything's cool. Here's our GW5, which is the pulse height, pulse width calculation, same peaky pulse. There's the ripple, there's the beat frequency that our customer was unhappy about. And you know, I can understand why. A lot of variation. The average value was correct, but when he's trying to read that with his data logging equipment, that's a big problem. So I'd say on average it was right, but it had a lot of beat frequency ripple in it, and it was because of the rate that we did the pulse height, pulse width modulation beating against the harmonics in the signal. Or GW5, this is actually a watt bar unit that had a little different sampling rate because we were doing watts and bars in the same transducer. But again, we got this beat frequency. And we were able to correct that by moving the internal frequency in our transducer away from the harmonics of 60 hertz. That's basically what we did. How are we doing on time?
Got 12 minutes.
12 minutes. I'm at my summary slide. Again, what I was trying to present in this presentation here was that measuring power is not, it can be problematic when you're trying to measure the power on the input side or the output side of an inverter. Currents can have very high crest factors, and I said may have harmonics. To your point, depending on the load, the current may have the harmonics filtered out because of the inductive nature of the load. The voltage typically will not. In fact, they get almost amplified because the inductive nature of the load tends to give voltage kicks and things, and even makes the voltage waveform even harder to control. Press factor can be up six or more. This can be a problem. So the output voltage has harmonics. An RMS meter may be what you want if you're trying to measure the voltage of current waveform, but you got to appreciate what it is you want to measure. If you want the RMS content of the whole modulated waveform, then you want an RMS meter. If you want the RMS value of, I'll say 60 hertz per synthesized waveform, then you probably want an averaging meter or a filter on it so that you get rid of the high frequencies when you use your RMS meter.
On the input side, the RMS meter will work fine, or does it back?
Input side, it should be fine.
Okay. Now, on the output side, you said voltages were issues. What do you do for EMI RFI type broadcasting? If you're trying to control that.
That could be an issue. It's more of a problem with the inverter design and how they handle their filtering or whatnot.
Well, yeah, because that's a voltage related thing.
Oh, it is. On the transducer side, we have to be very careful with our filtering and whatnot to suppress unwanted transients coming into our transducer. We actually purchased for testing purposes a very inexpensive inverter. I'll tell you what, when we turned that on, it would screw up every meter in our lab. I mean, if you ever, literally. Whereas you could get a higher quality, better designed inverter that would not do that. So again, it's more in the inverter design, but if you're an equipment manufacturer, you got to be able to live in that world. So again, noise suppression on your product and whatnot. But yes, we actually use that inexpensive inverter as a noise source to check out our equipment.
Well, yeah. Part of it was how do you deal with it, and you filter it at the input?
We filter it at the input. Yeah. And again, I pointed out that it's possible to use averaging responding meter to measure the fundamental. We get into a lot of other interesting situations, and again, my compressor experience is where a lot of this came from. You know, they no longer just go from 30 hertz to 90 hertz. They basically soft start compressors so that you minimize the inrush. So we're talking, now they want to make measurements down to 2 hertz.
Really?
Oh yeah. So from an equipment manufacturer now, if you're using a current transformer or something as an input sensor for your watt meter, now you got to start worrying about
Efficiency of it.
is it even going to work at 2 hertz? And then on the high end, 400 hertz. So soft starting can be an issue to the measuring device, again, because the frequencies vary so much. Anybody had any challenges or anything in the motor world? Do you get involved in?
I'm actually an IT. I'm liaison with the engineering department.
Yes.
We're going to start doing that, and we need some help with that. We're putting a scroll out in our HVI or rooftop units for India. They go in the train. We're using an Oztec inverter, and we're just going to start collecting data and getting the watts and temps and start doing that qualification. So, like, giving you a call.
That's right. You say that's a compressor or
Yeah, it's a
refrigeration
scroll.
or
It's-
air conditioning?
Yeah, so just a unit about that big for top of a locomotive.
Oh, locomotive. Okay.
Yeah. And we have to use an inverter because locomotives are DC. So we have Oztec make an inverter for us, and then we use a scroll.
Just use a DC one.
Tell Copeland that. That'd be easier.
All right. Well, I appreciate you coming. Hopefully we shared some things that can be helpful.
I think it's good.
Thank you.